So let's do an optimization example. This example says a 10-inch long pipe cleaner is bent into the shape of a rectangle. What dimensions of the rectangle will produce the rectangle with the largest area? So I always say let's draw a picture. So we're talking about a rectangle. And since this is an optimization problem, I asked myself two things. So first thing, what are we optimizing? And we want largest area of a rectangle. So we need some sort of equation for this. We know that the area of a rectangle is length times width, and I can label my rectangle accordingly. So I want to know, what am I optimizing, and then also what is my constraint? So in this case, they said that we have a 10-inch long pipe cleaner. Now, if you imagine bending your pipe cleaner, that's going to be your perimeter. So my constraint is my perimeter. And we know that perimeter is 2 times the length plus 2 times the width. And I know my perimeter is going to be 10. So I'm going to say 10 equals 2 times the length plus 2 times the width. Your next goal is we want only one variable on the right side of my area equation. So I want to use my constraint equation to get my area equation to only have one variable on the right-hand side. So first thing I'm going to do with my perimeter equation, I'm going to divide both sides of the equation by 2 just to make it simpler. Now, like I said, it doesn't matter which variable we solve for. We are going to give our answer with both dimensions. So we just need to choose one. So I might solve for length. So I'm going to say length is 5 minus w. And then I can replace length in my area equation with that 5 minus w. I'm going to distribute the w to make it a little bit nicer when we do our derivative. Now that we have one variable on the right-hand side of our area equation, we are going to take the derivative with respect to width on both sides of the equation. So the left side is going to be derivative of area with respect to width. On the right-hand side, let's simplify. We get 5 minus 2w. Okay, so now that we've done that, we know we have a derivative equation. We know that the max area is where dA dW equals 0, because we have our area equation with respect to width, and we have derivative of that. So we know the max area is going to be where this derivative equation equals 0. So I'm going to replace dA dW with 0. And let's solve for W. At what width do I have my maximum area? So I'm going to subtract 5 on both sides, divide by 2, and we get our width is 5/2. Now, we know that this 5/2 is a critical value, meaning the value that makes my derivative 0. But let's check. Let's make sure that this is a maximum, not a minimum. So if I make a number line, I have 5/2. I know that this is where dA dW equals 0. And let's do tester points on either side of 5/2. So pick a number less than 5/2. I'll pick 0. I'm going to plug 0 into my dA dW. I get 5 minus 2 times 0, 0, which is going to be 5, and that's positive. So my graph of A is increasing before 5/2. Let's check something greater than 5/2. Maybe we'll try 5. If I plug into my dA dW equation, I get 5 minus 2 times 5, which is 5 minus 10, which is negative 5. So that shows that my A of W is decreasing after 5/2. So that means that at 5/2, I am going to have a maximum. So my max area is when my width is 5/2. So I'm going to say width is 5 halves. Now the question though is asking for the dimensions. So I need my length and my width. So I have a couple places I can plug in. Pick where it's easiest. I might pick this equation to find my length because we need both dimensions. So I'm going to say length is 5 minus w. So I'm going to say 5 minus 5 halves. That's just going to be 5 halves again. So my dimensions are going to be 5 halves by 5 halves. Let's get our units in there. It's going to be inches. So 5 ½ inches by 5 ½ inches. And that is the answer for this optimization problem.